Hello, everybody. Welcome to one guest speaking session in the ML Theory channel. Today we have Celia and Adarsh in the topic of rewiring graph neural networks. Unfortunately, I only have a small bio of Celia. I don't have Adarsh's bio, so I will just talk about Celia. She's a second-year PhD candidate at the CISPA Helmholtz Center. Sorry if I said it incorrectly, for information. And she basically focuses on challenges in graph learning, particularly in how input graphs serve as both data and computational models. Yeah, I guess that we can start. Celia, the scene is
Yes.
for you.
Thank you very much for joining me in this talk. And also thank you so much for inviting me, Aniel. This is an amazing opportunity to share our work. So the title of my talk is Rewiring Graph Neural Networks When Less is More and Structure Matters. So I've done this work in collaboration jointly with my colleague Adarsh and with our supervisor, Rebecca Burkholz. And the talk will have three different sections. So the first section will have a small introduction about graphs or graph learning. Then the next two sections will be about two papers that we have had accepted. That's why one of them will be When Less is More and the other one When Structure Matters. So, okay. So this is our two works that the first one accepted at NeurIPS last year, and the second one very recently accepted at iClear. So we're very happy about that. And this is us. Of course, you can contact us after the talk if you're excited about this work or excited about these projects that we are sharing. So as a bit of an introduction, I hope this is not too slow for everyone or too fast, or I hope that this is enough to understand the rest of the work. So what is a graph? A graph is a set of nodes that are connected via a set of edges. And in our case, we also work with attributed graphs, which means that each of the nodes, it could also be the edges, but in our case, we just consider the nodes having features, so extra features that give more information about each of the nodes. Now, in graph learning, our task is to predict a specific problem that we might have. So we could have a global label in graph prediction. We could have each edge having different labels in edge prediction, or we could have each node having different labels for node prediction. So as an example here, we could have a graph of different countries, and the edges could just mean something like being adjacent, but it could also mean the amount of diplomacy that they have between them. And the features could mean something like the GDP or different measurements that we have for each of the countries. In graph prediction, we could try to predict the whole world climate change level as an example, or anything else. Then for edge prediction, we could try to predict the trade between countries or how much trade per year each pair of countries have. And for node prediction, we could try to predict the well-being of each of the countries. So in my talk, we are going to focus on node prediction. So each of the nodes would have a different label. Now, there's other real-world examples where graph learning might be important, such as in chemistry or in biology, where molecules or proteins will have the shape of a graph. And also in things like traffic or in maps, where locations can also form different graphs with nodes that are connected via roads. But of course, there's many more instances where graph learning is applicable. Now we go back to node prediction, as I've said. So where do we get the training? There could be many graphs. For example, in graph prediction, where you have same thing as in vision, right? You have different images, and each of the images has a different label. Well, in here, you could have many graphs, and each of the graphs could have a different label. But in node prediction, we usually have other setups. So there's an inductive setup where you have a full graph that is fully labeled, so you can train on it. And then at test time, you get extra nodes and that are linked to your already labeled graph. And these nodes obviously don't have the label. And the second setting is transductive or semi-supervised, where you have a single graph and some of the nodes have the labels and some of the nodes don't have the labels. But you know all of the, let's say, all of the edges between each of the nodes, so that is known. And we are, again, focusing on this particular thing because we are going to modify these edges, so we need to know what the edges are from the beginning. So just saying that we are, inside of graph learning, we're focusing on node prediction, and inside of node prediction, we're focusing on semi-supervised or transductive settings. Now, what does a graph neural network learn? Well, it has to learn how to modify the input features into the output classification, or at least a node representation that we can later use for the classification or regression or whatever problem it is. We usually do this, or the main paradigm is by message passing. So in message passing, each of the nodes receive and aggregate information from their neighbors in different rounds. So in each of the rounds is one of the layers of the network, and this aggregation is what the network actually learns until you get a final node representation, and the number of iterations is also the number of layers. And this is what the graph neural network basically learns. However, this might have some issues because we are using the graph to propagate the information from each of the nodes to all of their neighbors, or all of the nodes that are connected to each other. So if the graph is not very good at propagating information, then this could be an issue. And there could be some limitations related to information flow. In this work, we are going to define two of them. One is oversmoothing and one is oversquashing. So I'm going to define them afterwards, but I just want to remark here that these issues might be because of the way that the graph is intrinsically defined or is given to you. However, what is given to you is also data. So it's used as a computational structure, but it still provides some relation and information, or some relation about how the nodes are connected, right? So it still means something. If a molecule has like the different connections, that the bonds still are bonds, right? They are still meaning something. However, they should or don't have to be a very good computational structure. So this is what we are trying to solve. And one of the solutions to solve these computational issues is to rewire the graph. So that means to modify the edges of that input graph. And you could do it by multiple criteria. In our work, we're doing it by two different ways. And this is how the talk will be divided. So the first one, when less is more, we're going to do some edge deletions by a specific criterion. And that's called spectral gap maximization. And the second one is called when structure matters. So we're going to think about maximization versus minimization, when is a good time to do each of those. And this is going to be related to the community structure of the graph and the feature similarity of the nodes. So this was the first part of the talk. Is there any question?
I don't think there's any like questions in the chat, at least from what I can see. I have one question though. Like, I guess you'll probably elaborate on this later, but is there any value to doing like random, like pruning of the edges, right? Because you're following some heuristic. Are these heuristics like far superior than random, or is random in some cases also sufficient?
I would say that doing it randomly can help, and in fact, well, there's also ways of doing it during training in a similar way to dropout, but being like drop edge, and it can improve, especially if there's some instances where the graph is in very specific ways that the graph could be. But this is well, the ways or the heuristics that we're using here are used to solve very specific problems that the graphs might have, right? So if you want to address these very specific problems, then you should use the heuristics, and random will not suffice, right? I don't know if others want to say something about this or agrees with me.
Yeah, I mean, essentially the same. Yeah, like, I mean, the criterion that we use does specifically promotes information flow. And since oversquashing is supposed to be a problem where the information is not getting through, so having a specific criterion would help us solve this issue instead of like randomly dropping edges.
Yeah. I'm going to describe what these issues are right now. So this is the actual part of the talk.
Okay, cool. Because I don't come from the graph neural network community, so I guess some of my questions might be a bit unfounded.
No, not at all. I mean, it's really relevant, actually. Yeah. All right. Thanks. Okay, so I'm going to start with our second work, which is called spectral gap pruning against oversquashing and oversmoothing. So now is the time to describe what these issues or these information issues are. The first one that I'm going to describe is oversmoothing. So in oversmoothing, you get that the node representations are more and more indistinguishable as you increase the number of layers. So as we've seen before, the number of layers also corresponds to the number of aggregation steps. And so if you get like each of the nodes have very similar representations, then they're not distinguishable anymore, and the performance can be great as you increase the number of layers. And this is kind of opposite of what happens in some other places or some other areas in deep learning, where you get advantages by increasing the depth most of the times, right? So we would also want to get these advantages, and we sadly sometimes can't. The second problem is called oversquashing, and is more related to these information flow issues that Adarsh was mentioning before. So oversquashing happens when there are bottlenecks in the network, and this can obstruct the flow of information. So the information gets exponentially squashed through a single edge, and then it gets potentially lost. And there are different ways of measuring it. It could be local measures of each edge, but it could also be like a global measure that tells you whether the graph has bottlenecks or not. And some measures are about curvature, so the curvature of the edges. But here we have we use a global measure, which is called the spectral gap. And when the spectral gap is low, then there are bottlenecks. So that is bad because the information is not flowing. And the spectral gap is the first non-zero eigenvalue of the normalized Laplacian, which is that formula that I have there. So it's just an eigenvalue. It's actually the subtracting the second one minus the first one, but the first one is 0. So in these cases, and well, a common way of mitigating this is by again adding some edges that can remove this bottleneck, right? So if, as you can see in the lower example, you have a very strong bottleneck there. So you're adding edges that can connect these two communities better. And then this is what spectral gap maximization means. This is our criterion. Now, there's some discussion about oversquashing and oversmoothing being, let's say, opposites of each other, because when you have a bottleneck and you add some edges, and you can get more oversmoothing because you're connecting more things together with each other, and that's usually the case. And in fact, depending on how you define these things formally, you could just define it as, okay, one is the lower spectral gap, one is high spectral gap, and therefore they are just opposites of each other, and that's it, right? But we want to be a little bit more thorough with it and say, is there actually a trade-off here? And we want to argue that there is no trade-off. It doesn't have to be, and it's not necessary to be a trade-off. So we want to argue by bringing forward a paradox from network science. And this paradox is called the Braess paradox. This Braess paradox says that in a network of roads, so just drivers and roads, if you add some roads, sometimes this delays everyone else that is, or everyone in the network that is driving. And this is a little bit counterintuitive, but it means that not all edge additions can increase connectivity. So there are some roads that are bad for everyone. And the contrary is that some edge deletions can increase connectivity. And there is also, this is for commute time, but there's also a Braess paradox for our quantity, the spectral gap. And this means that we are able to choose some edges to delete that also increase the spectral gap. We want to argue that this helps in mitigating both problems at the same time, and therefore they are not at opposites. So we want to show a very simple counterexample of this that shows where the spectral gap increases And in this case, it's the ring graph, where if you remove one of this middle edge that is defined there, then the spectral gap has increased and therefore is helping over squashing. But then the order of smoothing decreases, and we're doing this by a specific test bed. And so as you can see, the blue line that is the lowest, and therefore it takes more time for the smoothing to occur. And we not only test this in this very simple example, but also in other real-world data sets. So we see that this is the case with these deletions that increase the spectral gap. This is also the case. Now, we want to maximize the spectral gap by doing deletions. How do we do this? We are taking a greedy approach, which is also very common in these rewiring approaches. So we want to have a set number of modifications, and then we calculate for each of the edges of the graph what would happen if we delete it. Okay, if we delete it, does it increase the spectral gap or not, right? And then we maximize that quantity. So we want to maximize the deletion that makes it maximizes the spectral gap. And in our case, we also have a nice criterion to stop, because the Braess paradox, even though it happens in many cases, and actually there's some mathematical statements that say that it is quite common to get Braess paradox edges, but there's sometimes a stopping criterion where there are no more edges that increase the spectral gap, and therefore you could technically just stop. Now, calculating eigenvalues sometimes is quite costly, especially if you have to do it per modification and per possibility of deletion. So we have two proposals in our work. These are the specific two proposals that we have done in our paper. So there's one that is constant, and it comes from matrix perturbation theory. And then there's a second one that has more guarantees because it's a sufficient condition, and it comes from the paper that proves the Braess paradox for the spectral gap. And for the first one is the main one that we're proposing. And we can see here that the quality of approximation is actually quite good compared to other literature. And it's also kind of very fast because it's constant compared to other rewiring criteria or other methods. And now we also tried for benchmarks in graph neural networks, and we try this out. And we want to try things that usually have oversquashing, in this case, some long-range interaction benchmarks, and also some oversmoothing. So we are trying it in large heterophilic graphs, which I will explain what heterophilic is, but our method usually works better for heterophilic graphs too. Now, these edge removals are also related to lottery tickets, and lottery tickets in general, without them being graphs, are just prune subnetworks of a neural network that can be trained to achieve the same performance as a dense network. And then graph lottery tickets are a lottery tickets on the weights plus a pruned input graph. So you are removing both weights and edges of the graph neural network. And by our method, we are basically explaining, or we have a way of explaining why this would work in graph neural networks, because deleting edges can, in some cases, fight both of these challenges. So this is a possible explanation of why they can succeed. So this was our first work. Any questions? Yes.
Right. So the first question that I have is regarding the comparison between this method and a method called expander graph propagation. Perhaps you're familiar with it, where basically, so it's usually used in one application of GNNs, which is neural algorithmic reasoning. And what it does is like it alternates, like depending on the parity on the number of iterations, and it alternates between the original graph and a graph that is the Kylie graph that I think some specific Kylie graph that has some structure similar to the original graph. Do you have any comparison with that method?
I don't think we have a specific comparison, but I find it quite interesting that you're saying that you're doing, let's say, like one with the original one and one with the rewired one. I think that's actually a very neat idea, especially if you want to, as we've said, we are trying to address these computational issues, but you also need somehow the information that the graph is giving you. And we have, let's say, a bit of a concern, right? When we just rewire without any other, without taking into account basically the task, right, of or what we're doing, or the relational information from it. So I think it could be interesting to just do, for example, our method of rewiring, but just like in each of the a kind of iteration where sometimes you do the original one and sometimes you do the rewiring. So I don't know. Also, I've seen some work that that tries to transform the graph according to these expander graphs, and this is also because they have like nice propagation or like information flow kind of characteristics, right?
Yeah, they are kind of sparse, and at the same time they are dense, so it's kind of
Exactly. That's very counterintuitive, no? But yeah, you always have this issue of like, am I losing too much information, right? And at least in our methods are very like, they go for the specific edge, right? Like they go for the one that will maximize it. So maybe instead of like transforming the whole graph to make it more similar, even though it's another rewind. Yeah, I'm not sure we've compared with it.
Okay, cool.
Yeah.
I do have another question. So I was recently interacting with this tool called Weight Watcher, which is basically an application of some results from statistical mechanics applied to neural networks, in which they basically take the spectral density of each layer, and due to some results from physics, they can predict that according to some power laws, they can actually measure if the network has overfitted or is underfitted or is just properly trained without even needing data. Is there any similar things for oversmoothing and over squashing? So can you measure? Is there a way of measuring this in a trained network without using data?
Okay. For over squashing, it's usually just there are arguments about, or I mean, discussions about how to define these things. So this is actually like not the definition is mostly like still argued, right? Like it's still discussed, and our work is also one of the kind of stones in the whole picture where we're trying to advocate for a specific definition of oversmoothing or saying that this doesn't have to be the case. So for oversquashing, it's usually just the graph. So you just need the edges but no training or anything. And then oversmoothing, there's like many ways of doing it. And if you just do it by like without any training, then you're probably getting to the same conclusion as opposite of oversquashing. And then yeah, our method just tries to run something by like seeing what happens, right? Like these curves that I've just shown. Wait, I can just show them. These curves, they're not just running the GNN, but they're like a linear GNN, and then we're measuring something about it. So pretty sure that you could do other measurements, and there's a lot of papers that I'm not arguing that this is the right way or anything, right? But yeah, I don't know if this answers your question. It's a kind of general comment on these definitions and whether you could test them or not.
Yeah,
Others,
okay.
do you have anything to say about this, maybe?
I mean, I think you are right. So sorry, if I might just add. So yeah, I mean, so over squashing can be measured without training your network, right? It's just the property of your input graph. So one of the ways we can measure it is by the spectral gap. Like if it has a low spectral gap, then yes, over squashing is happening. We are not training the network. And for over smoothing, I think over smoothing happens because you're training your model and the representations, they are becoming similar. It's kind of like a feature collapse that happens in your regular neural networks as well. So I think you need to, like, I mean, at least like you have from your conventional wisdom, right? Like deep neural networks, you can have like resonance from up to 50 layers or 100 layers. But for GNNs, at least like because we train them, we know that we usually don't have more than 4 or 5 layers. So I mean, in some sense, it's like a common wisdom that GNNs will over smooth if you increase the layers. So it's like, you know, that this happens without training. But yeah, I mean, I don't think you can like kind of quantify if a network over smooths before training the network?
I mean, I think depends on how you define it, no? And there's work on it, definitely.
I mean, the linear GNN setup, we don't actually train a network, right? We just
Yeah.
use the node features and then perform like a ridge regression on those node features. So we are not actually training like a
We're
deep
not exactly.
neural network. Yeah. So
Kind of
this could be one of
Yeah.
So this could be one of the ways you can think of measuring over smoothing without actually training a network.
Yeah, but unless you like actually train it, then you will not know, right? These are all like kind of tests of how you define how they will smooth. Yeah.
Thank you. I guess we can move on. Unless
Awesome.
there are...
Yeah. Okay. So, whoop, spoiler. Okay. So for the second work, which is well, kind of related to the first question about how well I will explain it later. It's about this when structure matters. So we are talking about community structure here, and also feature similarity. And first, I want to define what homophilic and heterophilic graphs are because I need these definitions. So in homophilic graphs, the each node has more the probability that they are connected with other nodes with the same label is higher. So they're usually connected with nodes that are the same label, so similar nodes. It's like you're friends with someone and then you have like the same taste, right? Something like this. In heterophilic graphs, this doesn't have to be the case. So each of the nodes might get connected to other nodes that have different labels. So this doesn't mean that it's not informative. For example, we have two examples here of two graphs. One of them is very informative because even though all of the nodes are connected to opposite colors, but you know which colors they will be, right? All of the greens will be with all of the blues, etc. And in the lower one, you don't get any of the information because they are connected to like, diverse ones. Okay, now we want to ask in this work whether spectral gap maximization is always beneficial or not, or when is it the case that we want to address this issue of over-squashing, or if it shouldn't, or if we shouldn't add it, right? And we want to argue here that you might want to consider where your labels are in the graph and where your node features are in the graph. And if you don't consider them, then some catastrophic things may happen. So if you're trying to solve over-squashing, then you are solving over-squashing, but you're doing other things to the task that are detrimental. So we have here a very simple kind of graph. It's called the stochastic block model that I will be using to explain these concepts. And there's there can be more than two, but in this case, we just need two communities, the green community and the gray community. And they are connected. So each of the nodes are connected to the same color or the same community with a high probability, and to the opposite community with a low probability. And that is why it's like more knitted with the same color, and it's like less when it's across communities. I hope that was clear, but I think from the picture it's kind of easy to see. And we are also having feature distributions, so we add a feature to each of the nodes, and so each of the communities has a different mean of their distributions, right? So they are different, they are separable kind of. And we want to argue that, this is proved that spectral gap maximization reduces the strength of the community structure, and that spectral gap minimization, so the opposite, or if you were choosing edges that minimize the spectral gap, increases the structure. So we can see it here, what happens. So first example, the community structure is less. And then second example, obviously very exaggerated, but there's a lot of, the community structure is very strong. And the main insight is that if your labels are the same as the community labels, so if the colors are the things that you want to predict, then reducing the strength of the community structure is or should be bad. It should be detrimental. And we call this setting the align task graph. So it's a high task graph alignment. And if this is the case, then maximizing the spectral gap should be detrimental. So we have some theory for it. So we have proved this in this SVM, in this stochastic block model. First theorem says that less pronounced community structure corresponds to a higher spectral gap, which is exactly what I've said in the previous slide. It just means that when you reduce the community structure, you have a higher spectral gap and vice versa. Now, same thing that I've said in the previous slide, if you reduce the community structure and you have a high task graph alignment, then this should harm the performance because you're reducing. So these communities have some information about your task, right? So if you're reducing it, then you're reducing the performance or you're reducing the information that the graph is giving you. And finally, we're doing this for different alignments, not only for a high task graph alignment. So forget about this formula that is scary because it's just very intuitive. If you have high alignment and very clear communities, then you will obviously have a low error, but this obviously depends depending on changes depending on the alignment, right? This is exactly what this formula is giving you, just a quantification of the other two theorems. Now we also support this with some experiments. So we test the accuracy not only for this kind of theoretical setting, but also for actual GCNs, and we find the same conclusions. And also we find that if we apply these rewiring strategies by maximizing the spectral gap, it eventually detriments or it harms performance, especially in these homophilic cases. So graphs that are similar to these SVMs or stochastic block models because they are connected to the same, the nodes are connected to the same labels. And as you can see, as there are more and more edges added, then the performance decreases. So one of the ways in which this high alignment is giving you this extra information is because the nodes, or we can assume in these specific cases that there are, well, in these failure cases, that there is some feature denoising happening. And by doing this rewiring, you are messing up the feature denoising. When the nodes with similar features are connected, then there is a variance reduction. So the variance of the feature distributions gets reduced, and therefore it improves the overall performance. So this is the mechanism that is getting harmed by doing this rewiring method. Now we want to propose some kind of method that could take this into account, or at least that will not have these failure cases. And for this, I know that this is a little bit confusing, but we are proposing 3 different ways, or three different methods. And then third one is a combination of the first 2. So the first one is community structure. We're just picking edges from the communities and then increasing the community structure or decreasing the community structure. So it's like a very direct way of addressing the community structure increase or decrease, instead of doing it by the spectral gap. But we're doing it just by the communities and in a more random, just drawing the edges from these edge areas. And not only from the communities, but also from the intra-community, so pairs of communities, the edges that are between communities. Now, the second way, or the second method, is called feast. So the names are very funny. Feast is just a feature similarity maximization. So we choose to delete, or we choose to add the edges that will maximize the overall feature similarity. So we want to address with this method this feature denoising that I just mentioned in the previous slide. So this is what we are trying to address with feast. And now in Comfy, we want to do kind of both things at the same time. So address communities or these different edge areas, and also doing the feature maximization in each of the areas separately. I hope this is clear enough. But the main idea, so I don't have to go deeper into this, the main idea is that we want to combine this community structure with the feature similarity so that we still keep the feature denoising, but we do it with respect to the communities that the original graph already has. So we compare with the other methods from our other paper and also from the ones that we had compared before, and we get some insights. So different data sets behave differently, and of course we're not claiming that the specific rewiring works for all of the data sets in the world, but we are figuring out cases where you shouldn't use them, or were cases where you should use ones more than others, right? So this is the line of the spectral gap maximization. And then we find that global feature similarity maximization boosts performance mostly for homophilic graphs. So the ones that I've said that are connected to the same label, or the nodes are connected to other nodes with the same label. So obviously you are already assuming that they have the same label. So this is just overall improving the performance from that. And the combination works better for heterophily. So this is the third example, Comfy, or the third method is or can avoid some failure cases too about just doing global similarity. So it has the best of both worlds in a way. And then finally, that this is something that is reassuring for the other work that we've done before, that mostly adjudications are effective, or at least most effective. And finally, I will ask for questions afterwards, but I just want to do a quick summary of what we've talked before. So we are rewiring the input graph, and for this, this could be a way to speed up training of a graph neural network. And adding edges is usually worse than deleting edges, because you're not getting this efficiency boosts, but also we are providing reasons, at least in our first work, where these removals can be advantageous in other settings too. And then I think the main idea, or the main focus that I want everyone to have from this talk, is that we are trying to, or we should be in the future, reconciling what the computational structure and the data structure means for graph neural networks. And rewiring, or the ways that we are doing rewiring, exclusively addresses these computational issues, and because the computational structure that the graph neural network is using is not the best one, is not the optimal one. And by trying to incorporate the features or incorporate the task, we're trying to avoid some failure cases of the other methods. But of course, there's a lot of work, for example, on graph structure learning, where they just try to learn what the structure should be during training, or in other ways. So a lot of work on this. And for the future, we would like to explore specifically what the input graph means and how it affects training. So to me, it can affect in two different ways. It can help, but it can also prevent things, right? We can learn from the input graph, but we can also get some blocks from it. We can it can prevent us from learning other things. So this is overall a nice idea to work for the future. That's all. As I've said before, we are very open to getting questions, and please contact us if you're interested about our work. And thank you very much for watching and listening.
Great. Great talk, by the way. I guess that we can stop the recording so that people can ask more questions. And let me first stop, and then I will ask a question.